Hi everyone and welcome to a new video about noise analysis in op-amp circuits. This is our example number 9. In this example we will look at a 3-stage amplifier. So we have 3 separate stages in cascade. Of course we'll look at our calculations step by step and verify these in simulations in SPICE. So let's look at our example. We have the following 3-stage amplifier. We have 3 inverting amplifier in cascade and we have 6 resistors. R1, R2, R3, R4, R5 and R6 and 3 op-amps. Each of the op-amps are OPA 209. So we have the values of the R1, R2, R3 and R4 etc. They're all shown here. What we'd like to know is the calculation of the input referred RMS noise voltage and also the output referred RMS noise voltage for this circuit. So let's look at our solutions. As we did in the previous examples, we look first to the op-amp specifications and let's look at some important values and also the graphs from the datasheet of this op-amp OPA 209. So we have the following graph which shows on the left side here the input noise voltage spectral density, and this is the input noise current spectral density on the right side. And several important parameters also shown here in the table, and we will use that later for our noise analysis. Now the first important parameter is the DC open loop voltage gain, which is given here as the symbol, has a value of 132 dBs. It's also shown here in the table, and that is a value here in the table. Which also have as a very important parameter the gain bandwidth product, which is then here 18 megahertz, and that is also shown in this table. Now in addition we have of course the very important parameters for the noise, the broadband noise voltage spectral density given by this symbol. It has a value of 2.20 nanovolts per root hertz. That is shown here. In addition it is also shown here because it has of course this unit. It's also shown here in this graph. That's the part which is then a flat part, which is then frequency independent, but that's why it's called broadband. Now in a symbol form you have the broadband noise current spectral density given by this symbol. It has a value of 500 femtoamps per root hertz. That's also given in this table for a specific frequency in these units, but also shown here in the graph for the input noise voltage spectral density. You can see it is 0.5 picoamps per root hertz, which is of course exactly equal to 500 femtoamps per root hertz. In addition we have the 1/f noise spectral density specified at some frequency, so that's actually this part which is frequency dependent. Now given by this symbol, it has a value of 20 nanovolts per root hertz at this frequency. You can see at 0.1 hertz it has a value of 20 nanovolts per root hertz. And in a similar form we have that for the 1/f noise current density at the specific frequency, again given by this symbol, it has a value of 3.75 picoamps per root hertz. Again at this frequency, looking here, you have this value which is also shown here. Those are the very important parameters we will use in our noise analysis. So let's look at the next step, which is the circuit performance. So what kind of performance we have in terms of gain? Of course the signal gain and also the noise gain. And what we have as a bandwidth, also the signal bandwidth and also the noise bandwidth. We will use of course this for our specific noise calculations, but we also need the signal bandwidth and also the noise signal gain and also noise gain for calculations, since this is a multiple stage amplifier. Now let's first look at the first stage, which is this part. You can see the signal gain is of course given by the inverting amplifier formula, which is the feedback resistance divided by the input resistance. You have the minus sign giving the inversion, so it is the minus 30,000 over 1000, that will be minus 30. Now the noise gain is always of course looking from the non-inverting amplifier. That's the definition. You disable your input signal, that will be the 1 plus the R2 over R1. The formula for the non-inverting amplifier, that will be 31. So it is in absolute sense a little larger than the signal gain. The signal bandwidth for specifically only the first stage is the gain bandwidth product divided by the noise gain, and if you do the math here you will get very close to 581 kilohertz. Now the second stage in a similar form, this part, again this is an inverting amplifier. You will use the same formula as here, so it is a signal gain for the second stage, minus R4 over R3, minus 5000 over 1000, will have minus 5. Noise gain again defined from the non-inverting input, 1 plus R4 over R3, you will get 6. So it is in absolute sense also a little bit larger than the signal gain. The signal bandwidth specific for the second stage only will be again the gain band product of this op amp, again the same op amp, divided by the noise gain of the second stage will be 3 megahertz. Now in the similar form for the third stage, only this part, again inverting amplifier, do the math for yourself, it is very straightforward. Again a noise gain defined from the non-inverting input using the non-inverting amplifier formula, and also the signal bandwidth. So you will have then 6 megahertz as the signal bandwidth. Now what you see is actually the following. You have the different signal bandwidth for each stage, and since these are of course in cascade, we will have to look at this in more great detail. Okay, let's first summarize what we have. The signal bandwidth of the first stage is much smaller than the signal bandwidth of the second stage, and also this first stage has also much smaller bandwidth than the third stage. Now since these are of course in cascade, then we have following. Thus we have 3 stages in cascade. The closed-loop signal bandwidth of the second stage and also the third stage is limited by the closed-loop signal bandwidth of the first stage. So the complete circuit as a first approximation can be, using the first order circuit approximation, be determined by the signal gain of the the signal bandwidth of the part which is the smallest. So in this case, it's the first stage. Now, using the break wall conversion factor for the first order system, which is then given by K sub n over, which is then pi over 2, that will be used to convert our signal bandwidth to noise bandwidth. So the closed-loop noise bandwidth will be then this conversion factor times the signal bandwidth of the complete circuit, which is then in this case defined or determined by the first stage. Now if you do the math here, you will get 912 kilohertz. That is the noise bandwidth that will be used for all parts in our circuit. Okay, let's move on to the total noise. Total noise is of course determined by each section of this circuit, but the noise of the first stage, that is the definition. The noise of the first stage will be multiplied by the noise gain of the first stage, but it will be multiplied by the signal gain of the second stage and also the signal gain of the third stage, because when you consider only the contribution of the first stage, you will consider the second and the third stage as noise free. Now, in similar form, the noise of the second stage, only this one, will be multiplied by its own noise gain, but it will be then the multiplication by the signal gain. So this will be then also noise free looking from here. So it will be actually from the input all the way to the output, and from the first one it will be from the input all the way to the output. Now in the similar form, you will have of course now looking only for the third stage, that will be only multiplied by the noise gain of the third stage. So this is a procedure we will use later on to determine the total output referred elements noise voltage. Now in general, very important note here, the noise source will be multiplied by the noise gain of the stage it is connected to. So actually this is the first stage and the noise sources are connected to this part, but it will be multiplied by the signal gain of the subsequent stages, which will be then considered as noise free using of course superposition principle. So if you convert this to the model of this op amp using the noise sources for each op amp that can be shown here, then we will use superposition and the calculation will be then carried out using the following steps. Now we will need to calculate the output noise voltage of the first stage, considering the second and the third stage actually to be an ideal amplifier, so noise free. Then we will do the output noise voltage of the second stage only, considering the third stage to be an ideal amplifier, so it is noise free. And then we will calculate the output noise voltage due to the third stage only, so we will have actually each separate stages separately contributing in the output, and we will add them up. Now that will be combined of course not in a linear form, but it will be used as a root sum of squares because we are considering noise powers. Okay, that will be then the procedure. So the notes in order here: noise from the first stage can be slightly reduced by the bandwidth limit of the second and the third stage. So this slight reduction in the noise bandwidth, that will be also have some effect of our total output noise voltage. So each stage will of course create its own pole frequency, but if you combine them together, those three poles in this form will have some effect, and that will cause some pole shifting. That will also reduce the actual bandwidth of the circuit. We will see that later on also in our simulation results. Now, for our analysis, we will use a rule which is when you have a several amplifiers and cascade, the noise bandwidth is approximately equal to the lowest noise bandwidth. That is just a very general rule. Of course, there are some exceptions. However, some of the higher bandwidth amplifier still roll off some noise. So it is a little bit, you need to be careful. So this is not the absolute rule to take into account, but it will work for most of the time. The first stage, that will be given by this. So this is actually the contribution of the first stage of the output. So this is the output noise voltage due to the first stage only, considering the second and the third stage as noise free. You can see it is multiplied by the noise gain of the first stage, by the signal gain of the second stage, and also the signal gain of the third stage, times the input referred RMS noise voltage of the first stage only. Now, if you now look at the second stage, it has only the noise gain of the second stage, but the signal gain of the third stage, and of course multiplied by the input referred RMS noise voltage of the second stage only. So you don't actually consider the first stage at all. Now, if you look at the third stage, that will be then of course this. It will be only the noise gain of the third stage times the input referred RMS noise voltage of the third stage. So those three values we need to calculate separately and also add them up using root sum of squares. Okay, that will be done. Let's look at the first stage first. The input referred RMS noise voltage for the first stage is composed of three parts. It is the input referred RMS noise voltage due to the internal op-amp noise voltage source. That's this one, due to the model. Also the contribution by the noise current source of the op-amp. And you have of course the terminal noise due to the resistors. So these are all given here in the symbol with the subscript 1, 1, 1 for each, denoting the first stage. And these will be combined again using root sum of squares. So this will be the total input referred RMS noise voltage at the first input stage. So this is the first stage. Okay, the input referred RMS noise voltage due to this source. So this is actually the voltage source of the op-amp. That is on its own also composed of two parts. We have seen that in a plot in the first discussion. We have the broadband region and also the 1/f noise region. So broadband and also the 1/f noise region. Both are given in the RMS value, so we need to calculate them also. And the effective value of these two, again, will be calculated using the root sum of squares. So we need to first determine the broadband noise voltage. That is then determined from the op-amp specifications. So for that we need the input referred RMS noise voltage spectral density and also the noise gain. So from the datasheet we had 2.20 nanovolts per root hertz, and also our noise bandwidth was calculated to be for all stages 912 kilohertz. Now if you now do the math here, you will get 2.10 microvolts RMS. Now for the 1/f noise voltage in RMS, you will have this formula. For that we need the normalized voltage, noise voltage, we need the upper cutoff frequency and also lower cutoff frequency. Now the first one will be also the closed loop noise bandwidth, so this will be 912 kilohertz. F sub L1 is actually a selected frequency to calculate also the normalized 1/f noise voltage. For that we need to also use the datasheet. Now this will be just the value we need to take in that 1/f noise region. It is most of the time taking as 0.1 hertz. So that's actually also what I have done here. Now, if I now look at the op-amp specification again, you can see this is the 1/f noise voltage spectral density. At this frequency, it is 20 nanovolts per root hertz. If I now use this to calculate the normalized noise voltage given for this part, that will be this formula. Using this symbol here, just specific for first stage, and then the square root of that 0.1 hertz, you will get 6.325 nanovolts RMS. I will now substitute that in here, and also the noise bandwidth in here, and also the 0.1 hertz here. That is shown here, and the result is 25.3 nanovolts RMS, or in microvolts as shown here. Now, we need to combine now, of course, to get here the broadband part and also the 1/f noise part. Let's then add them up using this formula. You will have then the following results, and you can see that the result is very close to actually exactly the same in this case to the broadband noise voltage. So the broadband noise voltage is dominating for this case. Now, we will also look at the contribution of the noise current source of the op-amp at the input as a RMS voltage. So it will be calculated by the equivalent resistance, that is actually due to that R1 and R2, and also the noise current source of the op-amp, which is then given by this in RMS. And then we will of course first calculate the equivalent resistance seen by this source, and also use the Ohm's law just to multiply these two, we get the voltage. The IN1 on its own is also composed of two parts. We have seen it also in the datasheet. It has also its broadband and also the 1/f noise part. So again, that will be combined using root sum of squares, and you will get the effective value using this formula. So the broadband noise current given by this symbol, and again we will look at the datasheet for that one. Again, very similar formula as we also used for the broadband noise voltage. This part is shown here for the specific for the first stage. And noise bandwidth, of course, was 912 kilohertz. Now if you do the math, you will get 478 picoamps RMS. Now for the 1/f noise current, a very similar formula. This is the noise bandwidth. This is the selected frequency. Again, we will take the 0.1 hertz. And this is the formula, this is the value for the normalized noise current that will be, of course, calculated using the frequency we have selected from the 1/f noise region. Now, I have this symbol, which is then the value at that 0.1 hertz in that 1/f noise region. And if I now substitute the values, I will get this result, and I will then use this in here using the noise bandwidth here and also the 0.1 hertz as the selected frequency. Now, if I now do the math, you will get 4.75 picoamps RMS. This is the broadband, and this is the 1/f noise part. Now, using the RMS values of these two, and also the formula for the I sub N1, then I have the following results. So you can again see that the broadband part is dominating here. So it is in total 478 picoamps RMS. Of course, we need to also calculate the equivalent resistance for the first stage. That will be just the 1,030,000 kilo ohms in parallel. That will give you 968 approximately ohms. Now, using Ohm's law, multiply these two, you will have 0.462 microvolts RMS. That's actually the second part of the input noise voltage contribution of the first stage. The next one is the thermal noise voltage, which is then due to these two resistors. So it will be calculated by the thermal noise or the white noise formula. Of course, this is again given by this expression. I need the R, which is then of course the equivalent resistance, and also I need the noise bandwidth, which is also see as the K and T. K is the Boltzmann's constant given by this value. T is the absolute temperature in kelvins, so it is in room temperature, let's say 27 degrees. It is a round number, T will be 300 kelvins. R again is the equivalent resistance in ohms seen at this node, and also the noise bandwidth given in hertz. Okay, in our case we have the equivalent resistance of 968 ohms, and our noise bandwidth was 912 kilohertz. If I now substitute these two values and also the Boltzmann's constant and the temperature, I will have in this part the following result. So I have 300 Kelvin, the resistor, noise bandwidth, that will result in 3.82 microvolts RMS. That's actually the part due to the resistor only. So the total input referred RMS noise voltage for the first stage will be then, again, calculated using the root sum of squares by these formula. Okay, the first part was due to that input noise voltage sort of the op-amp that resulted in this 2.10 microvolt RMS. Due to that noise current sort of the op-amp, we had 0.462 microvolts RMS. And due to the resistors, we had a terminal noise voltage of 3.82 microvolts RMS. Now these will be combined, and using this formula you will have the effective value at the input as the input referred RMS voltage for the first stage. Now if you do the math, just substitute the values, you will have 4.39 microvolts RMS. Now for the output referred RMS noise voltage, just looking from the input stage for the first stage, that will be again of course calculated using a noise gain of the first stage, which was 31, so 1 plus the R2 over R1. It will be of course also multiplied by the signal gain of the second stage and also the signal gain of the third stage. Now these are given here 5 and 2, of course in absolute sense. The input RMS noise voltage of the first stage just calculated as 4.39 microvolts RMS. Now we can now use the formula we have discussed earlier. This is the output referred RMS noise voltage due to this first stage only at the output of the total circuit. Noise gain of the first stage times the signal gain of the second stage times the signal gain of the third stage times the input RMS noise voltage of the first stage. If I now substitute the values, I will have 1.36 millivolts RMS. So that is the contribution of the first stage only, considering of course the second and the third stage as noise free. Now in a similar form we will now do that for the second stage and then for the third stage. Now second stage, again we have the input referred RMS noise voltage composed of 3 parts. I will now go a little bit faster because we have seen already this one. This is again the input referred RMS noise voltage due to that internal noise voltage source of the op-amp and also the internal noise current source of the op-amp, and also the resistors R3 and R4 will contribute at the input. So these will all of course add together using the root sum of squares. Then you have the contribution by the noise voltage source of the op-amp. Again, it is composed of 2 parts, the broadband and then 1 over F noise part. Using this formula, you will have the effective value of these two. Again, the broadband noise voltage, using, of course, now the noise bandwidth of the second stage will be just the noise bandwidth of the first stage, because this has, of course, the lowest noise bandwidth, so that will be 912. Now, again, using the op-amp specifications, you get exactly the same results also as we had for the first stage, so I will go a little bit faster. You can see all the values for the 1 over F noise part and also the broadband noise part are exactly the same as before. So I will just go very quickly to the end result, and that will be 2.10 microvolts RMS. And you will see it is then again the broadband noise voltage which is dominating. Now let's also look at the input referred RMS noise voltage then, due to that current source of the op-amp. Again in a similar form, we will look of course the equivalent resistance. That will be different of course, because now it is 1 kilo ohm and 5 kilo ohms, so it's different. And we have of course again the RMS noise current source due to that noise current source of the op-amp. Again, this is the equivalent resistance seen by this source, and we have the Ohm's law to calculate the input referred RMS noise voltage from the current and the resistors. This is again composed of 2 parts. We have already discussed this, the broadband and also the 1 over F noise part. Again, this formula, this is exactly the same as in the first stage, so I will also go a little bit faster. But now as a note, noise bandwidth for the second stage will be used for the first stage. So in the second stage you will use the noise bandwidth of the first stage because the first stage has the lowest noise bandwidth. So that will be also again 912 kilohertz. Again, using op-amp specifications for these values, I will also go a little bit faster again here. These are all exact same as in the first stage, so that will be the result. Now this for the 1 over F noise part. So that is the contribution of the 1 over F noise. This is the contribution of the broadband noise current. Add them up using the root sum of squares. You will have 478 picoamp RMS. Again, that is dominating part is the broadband noise current. Now, we will of course need to calculate the equivalent resistance. That is actually the only difference here compared to the first stage. That is 833 ohms. Due to that, 1000 and 5000 ohms as a parallel combination. Now, using Ohm's law, these two values multiplied, you will get 0.398 microvolts RMS. That is the contribution due to the input op-amp noise current and also the resistors, of course. Now, let's also look at the contribution of the resistors only. Of course, that is calculated using the white noise or the thermal noise formula for the resistors. That is shown here. And again, these are the specifications or the parameters. We have the temperature, we have the Boltzmann constant, we have the resistor R, and we have the noise bandwidth. Now, of course, we have again the noise bandwidth what we use here. That is for the first stage, but it is of course also valid in the second stage and also later on in the third stage. This is of course the equivalent resistance we have for this part. If I now just do the math again, that's actually also the only difference compared to the first stage, because the resistors is now changing and the rest of the values are exact same. You will get here 3.55 microvolts RMS. So it is a little bit smaller because the equivalent resistance here was a little bit different. Okay, now the total input referred RMS noise voltage. That is again calculated using the root sum of squares. Using this formula, I need these three parts, and I have already them. So this is actually the first, the second, and also the third one, which is just calculated. Add them up, and you will get this one. If you now do the math, you will have this, and that will result in 4.14 microvolts RMS. Now, going from here to the total output referred RMS noise voltage, just looking from the second stage only. For that, I need, of course, the noise gain of the second stage and also the signal gain of the third stage. That is given here. And also, of course, the input RMS noise voltage of the second stage. That is then 4.14 microvolts RMS, just calculated. Now, the output referred RMS noise voltage just from the second stage at the output will be then calculated using this formula. Noise gain of the second stage times the signal gain of the third stage times the input referred RMS noise voltage of the second stage. Now, if you now do the math, you will get here 49.7 microvolts RMS. So that is the second contribution. So we have now done the first and the second stage contributions at the output of this total circuit. The last part will be then due to that third stage. So let's look at the third stage. And again, we look at the op-amp model, and we have, of course, the input referred RMS noise voltage, which is again composed of three parts. And I will also again go a little bit faster because the input noise voltage source and also the input noise current source and also the resistors will contribute, and that's shown here in these three values. Now, these are then combined together again using root sum of squares. Okay, again, for input referred RMS noise voltage due to that noise voltage source of the op-amp. Again, it is composed of two parts, broadband and the 1 over F noise. And we go a little bit faster. This again calculated using this formula, effective value of these two. Broadband part. Now we need to again really be careful. Noise bandwidth of the third stage will be then limited by the noise bandwidth of the first stage. That is then this, because that was the smallest one. And again, we use 912 kilohertz. That's very important. So again, op-amp specifications, just substitute the values in here. You will have 2.10 microvolts RMS for the broadband part, 1 over F noise part given by this formula. Substitute the values. This is already done, of course, in the first round in the first stage. So I will go a little bit faster again, and you will have these values for the 1/f noise voltage. If you now combine them using this formula, you will have again 2.10 microvolts RMS, and again the broadband noise voltage will be dominating. Now the second part, just due to that noise current source, again we need the equivalent resistance, but in this case we have the 1 kilo ohms and 2 kilo ohms, so that will be different. But this will be of course again the same. So this will be again seen by this source, current source, so what is actually the resistance seen by the source. And we use the Ohm's law to calculate the input revert RMS noise voltage due to that current source only. So that is on its own, that current source is also composed of two parts, the broadband noise and also the 1/f noise. And these will be of course again combined using root sum of squares. And again, remember, noise bandwidth of the third stage will be limited by the first stage, so it will be then the noise bandwidth of the first stage. So the third stage, the stage 3, will have exact same noise bandwidth as the first stage. Again, 912 kilohertz. Again, we go a little bit faster because the broadband noise current is already done in the first part for the first stage. That will be again used here. Noise bandwidth just calculated here for the broadband part. For the 1/f noise part, we just substitute the values, and you will have 4.75 picoamps RMS for the 1/f noise part, and for the broadband part you have 478 picoamps RMS. Now we will use this formula to calculate the RMS value of this current noise current source. Okay, that will be again just the value of the broadband part. So the broadband noise current will be dominating in this case again. Now the only difference here in this third stage is again the equivalent resistance, which is then given by this, which is the parallel combination of the R5 and R6. That will be 1000 and 2000 ohms in parallel. That will result in 667 approximately ohms. Now using Ohm's law, multiplying of these two values, you will have then 0.318 microvolts RMS. That is actually the third contribution for the for stage 3. Now we need to now combine, of course, the resistors. So the contribution of the resistors will be of course calculated using the white noise or the thermal noise voltage. That's given by this formula. And again, these are the parameters: the Boltzmann constant, temperature, and the resistor and the noise bandwidth. Now in this case again we have this resistor, and now also the noise bandwidth will be limited by the first stage, also for the third stage. Again shown here to remind you that this is the noise band we will use. Now then we have, just looking for the third stage, we have then the values substituted in here. You will have 3.17 microvolts RMS, so a little bit smaller than the second stage because the parallel combination here is a little bit smaller than here. Okay, now the input revert RMS noise voltage just for the stage 3. Again using root sum of squares formula. This is the formula. We have of course the first part, the second part, and also the third part given by the thermal noise voltage by the resistors. And if you combine them, you will of course just substitute the values in here, shown here, and you will get 3.82 microvolts RMS. And in this case actually this part is much closer to that one, so that is the contribution of that one is of course most dominant. Okay, total output revert RMS noise voltage for the third stage. That will be calculated using the noise gain of the stage 3. That is just 3 because it is just looking from here and then using non-inverting amplifier formula. And you will need the input RMS noise voltage of stage 3. So this is then what we had just calculated using noise gain and also the input revert RMS noise voltage by the third stage. Using this formula, noise gain of the third stage times the input revert RMS noise voltage at the input of the third stage. And if you now do the math, you will get 11.5 microvolts RMS. So that is actually our part for the stage 3. So we will now combine them together. So the total output revert RMS noise voltage, which is again given by this symbol, is the contribution of each stage at the output. Now we have, of course, the stage 1 that was given by this value. Stage 2 has contribution of this, all in millivolts RMS, and the stage 3 has a value of this one. So it was 11.5 microvolts RMS, that is in millivolts this. Now if you combine them using this formula, just substitute the values, you will get 1.36 millivolts RMS. So what you see as actually the contribution of the first stage is most dominant, and the noise contribution of the second and the third stage is not that much, and actually you can just consider the first stage only. And that's actually why we most of the time design the first stage as a very low noise amplifier. So observations again, the total noise at the output of the circuit is almost determined by the noise contribution of the first stage. Now there are some notes important. The first stage is a high gain stage. So if it is a high gain stage, then the subsequent stages, so compared to the subsequent, then the first stage will dominate the noise performance of the total circuit. So if you have a high gain here, it's actually 30, just 5, and it's actually 2. This will dominate the total circuit noise performance. And because that is most of the time the case, the input stage will dominate the noise performance of the total circuit. Engineers will often use more expensive low noise amplifiers for the input stage, and not that much expensive for the second and the third stage, and also later stages. That's most of the time done. So the input stage will be most of the time designed as a very low noise amplifier. Okay, let's also look at the signal to noise ratio, SNR. That will be, of course, also very important. That's a measure that compares the desired signal level to the noise level. And if you do that in a little bit more accurate way, then definition is actually the ratio of the signal power to the noise power. And that is often expressed in decibels. So if you have a higher value of a ratio which is higher than 1, so in dBs it's larger than 0 dB, that indicates you have more signal than noise. And other way around, of course, if you have a ratio which is between 0 and 1, which is of course then a negative value in dBs, then you have more noise than signal, which is of course not what we want. So we would like to increase actually the SNR. That will of course have some better effect, better performance in terms of noise at the output. Now for this circuit, the SNR at the output for a specific frequency, we will see that shortly. Why is that called a specific frequency? Can be calculated using this formula. So again, this is directly given as in units of dBs or decibels. Now we had calculated 1.36 millivolts RMS. If I now just substitute the values, I will have 57.3 dBs. That's the result, and we will check this. Now let's then look at the simulation results. The frequency response first, and we will see the signal gain, also the bandwidth and the cutoff frequency. Now this is the DC gain. You can see the 3 stages. This is just the gain plot. We have the DC gain here and some labels. Now the DC gain, or the total signal gain, which is defined at DC, is given here as 49.54 dBs, and that is actually very close to the calculation, exactly equal to the calculation actually here, because the first stage was 30, and the second stage was 5, and the third stage was 2. Just using these figures, and you will then have, of course, in dBs 20 times the log of these 3 values multiplied, you will have 49.54 dB. So that's actually the nice result here. The cutoff frequency here is 555.3 kilohertz, but our calculations, of course, assuming that the first stage was dominating the complete circuit, so the signal bandwidth, just considering this first stage, was used as 581 kilohertz. So there is some difference here, and that's actually what we have considered before. Due to the second and also the third stage, which is also has its own pole frequency, the actual cutoff frequency will be slightly smaller. That will also cause some less noise. So this is the actual signal bandwidth and not this one. So we will see also some differences in the simulation results compared to our calculations. What's also important here to see is there are 2 labels here. So at 100 megahertz we have approximately minus 50 dBs, And at 1 gigahertz, so it is 10 times larger in frequency, so 1 decade up, it has a value of minus 110 dBs. This decrease in gain is 60 dBs, so you go from minus 50 to minus 110 for an increase in the frequency by 1 decade. So I can say the signal gain decreases by 60 dBs for a decade increase in the frequency. And this slope is actually has a value of minus 60 dBs per decade. And this is actually a characteristic of a third order system. And that is interesting because it is actually a third order system, but up to this point it can be considered as a first order system, but for higher frequencies it must be considered as a third order system. So that's actually what you also see here by using these two labels. Okay, let's also look at the input noise voltage spectral density given here. Again, the circuit, you can see the plot, and what you see also is that the very high noise for frequencies which is then larger than 100 megahertz. You can also see here, it's very hard to see, that part is actually the 1 over F noise part, and then the part which is then constant. So we have in summary actually 3 regions. The frequency dependent part, 1 over F noise part, that part, very hard to see because due to that large region here. And we have the part which is independent of the frequency, which is the broadband or the white noise part. And that part which is then increasing, which is the part due to that after this 100 megahertz. But that part is not really interesting for us because our complete circuit will filter out the signal much earlier. So that part is not really interesting. That is the input noise voltage spectral density. Now let's also look at the output noise voltage spectral density, very important. You can see again the 1 over F noise region, the broadband part. What you also see is actually the output noise voltage spectral density will approach a value which is 0. That is due to the bandwidth limiting of the op amps. So dependent part, 1 over F noise, independent part, which is the broadband part here, and it goes to 0 because the bandwidth limiting of the op amps. So if you didn't have any bandwidth limiting, this will of course just stay a constant at this value. Okay, that is another for this. We have now also the total RMS output noise voltage, very important because that was also one of the questions. In this case we see a simulation of 1.227 millivolts RMS, and you can see this is actually the settled down value. But we had calculated what was 1.36 volts RMS. So there is some difference here. So I simulated this one and I calculated that one. So what's the possible cause of lower output noise voltage in the simulation? Now the first order approximation is not valid anymore. That is for sure true because we just assume that this part, the input stage, will just determine the complete frequency response of the circuit. That's of course not true. So the noise from the first stage can be of course slightly reduced by the bandwidth limitation of the second stage and also the third stage. We have also seen that in the body diagram. So this is not really as surprising that this is lower than that one, but we need to of course calculate that in a more accurate way. So the estimation is not accurate. So we need to check this in more detail. So let's then do a better estimation of the total output noise voltage. Now, in theory, in a more precise way, we need to of course integrate the actual closed loop signal bandwidth of the complete circuit, which is not easy. But instead of that, we can use also evenly weighted average of the noise bandwidth conversion factors and then add them up to get to the average conversion factor for our noise bandwidth. So what I mean by that is the following. If you have the first order part, which is just this conversion factor which is used for the complete circuit, you can also add the second order conversion factor and also the third order conversion factor. These are the conversion factors. You can also find them also on the net. I won't go through it into details. This is just the value we will use. If I now of course then want to have the average of this one in evenly weighted form, I will just add them up. and I get the following results. So add them up and divide by 3, just evenly weighted, and I will get 1.317 as my average noise bandwidth conversion factor. So that is actually the actual noise bandwidth conversion factor I will use. Now, if I now multiply the signal bandwidth with this new conversion factor, I will have the new noise bandwidth, which is then 765 kilohertz. So it is much lower than the 912 kilohertz we have used earlier in our calculations. That will of course also result in less output noise voltage. So this is the new closed-loop noise bandwidth. Now, using this value, we get the following table. So I won't go through each calculation in great detail. So these are just the values for each stage. You can see it is lower now due to that lower noise bandwidth. And if I now see the output noise voltage for each stage, that's the first stage, that's the second stage, and that's the third stage. So you can see the contribution for each stage. If I now want to, of course, calculate the total of the circuit, what is then the total output noise voltage, again that will be calculated using the root sum of squares. Just take these three values in here. So that calculated, here you can see the details. You will have 1.246 millivolts RMS. The simulation gave 1.227 millivolts RMS. So this is much closer actually to the simulation. And that is then a better estimation actually of the actual performance, noise performance of the circuit. So just looking at the first order and using only the first order noise bandwidth conversion factor is not really that accurate in this case. So this is actually a way to get the accurate value of the actual noise performance of the circuit. So again, looking at the total RMS noise voltage and the output of the circuit, this was the result simulation. And this was the table we have just generated. Using this, we have calculated this value, and you can see this is much closer than that one, because we had here 1.36, now we have 1.246 here, much closer to the simulated value. Okay, as a final one, you look at also the signal to noise ratio, SNR. That is actually the part we have here. It starts off very high for the low frequencies and then goes down and then approaches actually a constant value. And we have calculated using this formula what the value was, and using this for the output noise voltage. Of course, this is now a little bit smaller. Now, if in our original case it was 57.3 dBs, but if I now look at the simulation, it is now 58.2 dB. So this difference is of course also due to that lower, actually what we have as higher output noise voltage. So if you of course use here the 1.246 millivolts RMS, you will get of course these two values very close to each other, but this is still very close to each other, the simulated and the calculated SNR values. Okay, that is now for our example using a third order or three-stage amplifier circuit, where we have considered the noise performance. We have seen the input, the output noise performance of the circuit, and also the signal to noise ratio. We have also looked at the body plot, specifically the gain, and also determined what the effect is of cascading three stages to the actual cutoff frequency, and then you used actually a better estimation to calculate the actual output referred RMS noise voltage for the circuit. That will be of course now our ninth example. In the previous example we have seen a second two-stage amplifier and then done the noise analysis. In the next examples I will also consider different problems, different topics like averaging of noise to reduce actually this noise, and also some specified problems. So if you have any questions about this example or any other example, please let me know and I will try to answer them as soon as possible. Thanks again and see you next time, and don't forget to like and share this video so that we can reach more people. Thanks for your contribution and see you next time. Take care.